Hi, I want to continue on with equilibrium expressions, in particular talk about three things. One would be why are there different kinds of k's that we talk about. We talk about k in a general sense. The book writes it as k subscripted c. Also talks about KAs and KWs, and I like to talk about something called KSPs. I also talk about some of the simplifications for the math that lets us solve what would otherwise be quadratic or even more difficult algebraic expressions. Anyway, we can make them quite a bit more simple with some intuitive simplifications. And then lastly, in this one, we'll talk about the common ion effect. All right, so straight away the K's. Our general expression for K is sort of a products over reactants thing, and it really applies to anything. All the K's follow the same rules. So an example I like to use is if we have nitrogen plus hydrogen, and that gives us ammonia, we just write our K as products over reactants, so that would be our NH3 concentration squared over N2 concentration, hydrogen concentration cubed. All right, so that one's old hat. Solubility product, or KSP, applies to ionic solids. And of course, when ionic solids dissolve in water, they dissolve to form ions. And so our KSP here is a similar format, except that the original material, let's just do our calcium fluoride example, because it's a solid, doesn't show up. Its concentration does not change. So my KSP for this one would just be the products. So calcium ion times fluoride ion squared. And again, the calcium doesn't show up because it's, or the calcium fluoride doesn't show up because it's a solid, and as it dissolves, its concentration doesn't stay, as long as it doesn't change, as long as we have excess solid there. All right, weak acids get particularly important in the last chapter, but weak acids are acids that don't ionize completely. So we hopefully remember that something like hydrochloric acid ionizes completely, but something like acetic acid does not. So my acetic acid, weak acids, my acetic acid dissociates to give me the free proton plus the ion, which is my C2H3O2, which is the acetate ion. And then the K for this is again products of reactants. Though in this case we have a denominator here. Nice thing about the Ka's is that we tend not to have any squared terms. It's all first order with respect to each of the three ions involved, or the two ions and the original acid. And then lastly, water is the dissociation of water to give me H plus OH minus. Water we consider liquid. The ions that form are aqueous. Should have done that up here too. And up here. Oh, getting lazy. And so my KW here does not include the water, but includes the two ions. So it's going to be my H plus and my OH minus. And this one, even though it's not something you really have to worry about memorizing, it's one of these things that we see so often, most people eventually just know it. That's 1 times 10 to the minus 14 at 25 degrees Celsius. Okay, so again, in all cases, they follow the same rules. It's products over reactants, only things with meaningful concentration show up, and that's pretty much it. We talk about these special cases because they're very important in some areas of chemistry. Solubility products can be very important in electrochemistry. Weak acid Kas can be very important in buffer calculations. And the Kw for water is very important in calculations of pH as well as buffer calculations. All right, let's do a couple of examples here. If we have a solution that's saturated with calcium fluoride, and we need to find out what the concentration of calcium ion is in that solution, how do we do it? So what we want to do is make sure we're clear on what's going on. So I've got my solid calcium fluoride, and some of this dissolves. And so I get some number of calcium ions, and for electric neutrality I have twice as many fluoride ions. But I don't know how many of either one I have. The only thing I know is that the fluoride is twice what the calcium is, that's the fluoride concentration is twice the calcium concentration, and I know that the product of the calcium times the fluoride squared is this 3.9 times 10 to the minus 11. So I have two equations and two unknowns. One of the equations is the chemical dissolving, and the other one is that some relationship of these guys gives me the CaF2. So I can do an icebox here. I like it for consistency, though it's maybe not completely necessary. So my initial of these guys before anything dissolves would be 0. And if I say X calcium dissolves, and I can say it's the amount that dissolves, I can say it's the equilibrium amount, I can say it's the change. It'll work out to be the same thing. So if I have X calciums dissolve, so maybe I'll say, whatever this guy went from, I lost X of that, it produced X calcium 2 pluses, and what's important is that for every X of calcium I get 2 X's of fluoride. So at equilibrium, again I have X and 2X. My K, which in this one is the calcium times the fluoride, is going to be X times 2X quantity squared equals 4X cubed, or X equals the cube root of K over 4. And if I pull out my calculator and work this out, what do I get here? So it works out that I get 2.1 times 10 to the minus 4. And remember, this is the concentration of calcium ion. That's what we defined X as. The fluoride concentration would be twice that. All right, so there's my answer there. All right, second problem, and this is something called the common ion effect. And you'll see its application, is that if I do the same thing, so I've got my pile of calcium fluoride in here, oops, and the difference here is that I already have a whole bunch of fluoride just floating around from the sodium fluoride. And sodium fluoride should be a strong electrolyte. So I have a bunch of fluoride that's already in solution, and as the calcium dissolves, I'm going to increase the fluoride by the calcium fluoride that dissolves here. So here's where the icebox really kind of comes in handy for a couple of reasons when it shows us where simplification gets important. But same reaction, I've got my calcium fluoride giving me calcium 2 plus the 2 fluorides. My initial, my change, and my equilibrium. Again, we don't really care what the calcium fluoride is. My initial calcium is 0, but my initial fluoride is 0.15, and that 0.15 is because that's what's floating around in the solution. All right, I'm going to let X of the calcium fluorides dissolve. That will increase my calcium by X and my fluoride by 2X. And so at equilibrium now, I have X calciums, and I have 0.15 plus 2X of the fluorides. Okay, if I wanted to solve this, I would have that my K equals x times 0.15 plus 2x quantity squared. That is going to lead me to some sort of a cubic polynomial, and I don't want to do that. Okay, that's difficult. But what I can do is recognize that x must be very small. Up in the previous example, we saw x was like 10 to the minus 4. Here, there's good reasons to believe it's going to be even smaller. So what that results in is that this quantity here is approximately equal to 0.15. And this is really a significant figure argument, that if x is really small and I add that to 0.15, I'm going to get something like 0.1500002, which to the 2 sig figs that I have really just simplifies to the 0.15. All right, what that does for us is gives us a much simpler term, because now it's going to be that K is going to equal X, the calcium concentration, times 0.15 squared, which means that X is going to equal, how's that going to be, 0.15, oops, it's going to be K over 0.15 squared, which gives me 1.7 times 10 to the minus 9. All right, so it might not be completely obvious why this is, but notice the magnitude of numbers here. Here my calcium ion concentration was 2 times 10 to the minus 4. When I did that same salt dumped into water that contained fluoride, not very much fluoride, 0.15 molar, now the calcium ion concentration can only get to 1.7 times 10 to the minus 9. So it's changed by 5 orders of magnitude. It's by a factor of 100,000. And again, the reason for that is just following the math, that the excess fluoride pushes the equilibrium back to the left here, and that drags the calcium out of solution to reform the calcium fluoride. All right, so these sorts of things, the simplification with KSPs, but also with other equilibrium calculations, saves you an awful lot of work. It makes problems that are almost impossible to solve relatively easy.